And then we started looking at it from the stringer crack issue, and really what kind of happened is, as we did that failure analysis, we looked at root cause, and you're trying to find the obvious thing. And from a schedule perspective, the best chance that we had to launch back in the window we had in November, December, was that if this was an obvious problem that was easily fixable. So we went off and looked, and you could tell right away from the imagery from that U-shaped foam crack that we knew a stringer underneath had probably cracked. We had never seen it before, but it was pretty obvious that that's probably what had done it. So when we scraped the foam off and we looked, and we found that that became the bigger problem for us in terms of being able to turn around and make launch. Yeah,
that's the video of the crack back on November 5th.
And you can see that U kind of encompasses one of those stringer hats, we call them, the little U-shape pieces that stick up. So the big part we did was take that failed part off. So the KSC team focused on a repair, while the analysis teams were off looking at all the other root causes. We had a fault tree team going. They call it a fishbone, because when you lay out the main path, you take all these little branch paths off, the possible contributors. It looks like the bones of a fish sitting on a plate, I guess. You can't even read it. It's so densely packed with lines right now. And we had the teams looking at manufacturing and build up, and was there anything unique about the loading event that day that maybe caused a problem? And what we were kind of looking for, again, we weren't looking for it, but the path that would let us get out of the woods quickly would be if we took that failed part off, took it back to the Michoud assembly facility in Louisiana, and found a defect that had escaped us. During manufacturing, a crack was introduced. It escaped our inspection processes and was delivered here to the pad with a crack or a flaw already in that stringer, such that when we put the stress of loading on it, the cryogenics in that oxygen tank, the crack appeared just as the level past that flange point, that stringer. The tops of those stringers correspond to a flange, a cord that bolts up to the bottom half of the LOX tank, the liquid oxygen tank. And so as the liquid oxygen hit that point, the tank shrinks. It shrinks in radius about half an inch, so diameter is moving about an inch. And so that stress caused the cord in the tank moved, but this stringer broke and didn't. So we say it popped out, but in reality it kind of stayed put, and all the rest of the stringers moved in. And when it stayed put, that caused the foam to displace as well. So anyway, back to the root cause. If that had a problem, then that would be you cut the failed part out, you repair that failed part, and then you go off and look to make sure you don't have any other failed parts on the tank. So our initial thought was, if we could find that initial flaw, this would be an easily understood problem. And since we're still here doing a tanking test, that obviously didn't happen. So the fractography, which is that investigation of the crack itself, showed no initial flaw. It basically showed that the cracks on stringer 7 and stringer 6 were all single event overload kind of stress cracks that basically instigated and ran in one shot. They didn't kind of start slowly and go. They just instantly cracked. That doesn't mean you couldn't have had an internal defect to the part somewhere, but there was not a through crack in the system anywhere. We also looked at the materials properties to make sure it was built right. It wasn't a bad batch of metal. It wasn't formed wrong. It wasn't heat treated wrong. None of that showed any problems at all. So really, we kind of lost our smoking gun type of theory and had to go to the more insidious, what else could it have been? And we've been slowly going along. Yesterday at the PRCB, the Program Requirements Control Board, our big shuttle program main board, we sat and talked about status to date, and it all started to come clear yesterday. In reality, it's been this last week it's all starting to come together. About 2 weeks ago, it kind of came together for us that we were going to put this into two separate families. Either the stringer was the cause of the problem, that there was some assembly tolerance, some buildup of stress in that part, or a crack that we just didn't go through the system and we couldn't see that caused this stringer to break. And so it's an isolated event, it's this stringer, and that's the problem. Or that's the other family is that the stringer was a victim here, and the design has a problem, the tank itself has a bigger issue to it, the loading had a problem, and that there's something wrong generically that's causing stress to be concentrated in this area that's never been there before, and then this crack is kind of a symptom of a bigger problem. Now, all our analysis and modeling shows that should not happen if a properly assembled inner tank and a properly mated structure should be fine, has plenty of margin actually, and that's one of the things that gave us pause, is those numbers showed to be we need a pretty big flaw to have caused this part to fail. So we were thinking we'd see something obvious. which is kind of why it headed us down that path. But anyway, so about 2 weeks ago, we kind of put those two in the family. And one of the best ways to kind of take that global, is there something else wrong with this tank that we don't quite understand, that the models don't show us, is to do a tanking test and do an instrumented tanking test. And so we kind of chose that option and kicked off. If you think about it, I think we put close to 90, almost 100 pieces of instrumentation on the tank, bonded them to both the plus and the minus Y, so both sides of the tank, ran the cables across the outside of the vehicle, put a whole bunch of dots on the outside of the tank to do some optics. All of that in a very short period of time. It's an amazing amount of work by the Marshall teams, the Michoud teams on the ET project to design what they needed, and then the Kennedy team to implement and put it on the tank and route it and be ready to go here today. Even as early as probably Wednesday, I didn't think we'd be sitting here Friday. I thought this would be Sunday when we were finally ready to go. So the guys did an amazing job. But the point of the data, to go back to your original question, is why are we here today, is to gather performance data on the tank. So we have stringers instrumented in the repair area, so we can look and see how that repair performs under a cryo load. We have stringers instrumented next to that repair that aren't damaged, and so we can see how they perform. That'll give us some information about the general area around this local area to see if there's any non-linearities. And then on the opposite side of the tank, we've instrumented stringers to kind of go to a control type theory to say, over here in a completely different area, here's how the tank performs. And really what we want to look for is, in addition to the details of the data, it's really that big picture of the data. Does the left side and the right side of the tank compare to each other? Are they performing in family? Do both sides perform the way the models show they would? 2 points to this test. One is to gather data that we don't have to kind of ground our models. The other is we have pretty good models. Do they perform properly? So, we're looking for non-linearities. Is something obviously not tracking what we think it's going to? And then the performance of all these strain gauges and thermocouples kind of, are the temperature profiles what we think? Is there a spike in stress or strain that we do not expect to see? That would be an indication that there might be a different problem other than the stringer itself having a flaw or a defect that would put us in that second category, or second family, where the stringer was the victim here, not the cause. None of our experts believe that to be the problem. None of our analysis or data mining to date shows that that's going to be the case. This tanking test hopefully will give us the final set of data that lets us kind of declare that to be true. And now we can focus in on that first part. So there's a very long-winded answer to your first question.
Okay, well, but you even after all this, you don't expect to get that data right away today, unless there's something really obvious like gushing gup or foam that cracks. You're not expecting results right away. I mean, you've got a lot more analysis to do, correct?
Yeah, you're right. So the gup is pretty much a 1 or a 0. It's either going to leak or it doesn't. So that's a good test, and the team's very confident that that's not going to happen. But we'll get a good check on it today. If another stringer would crack such that the foam pops, we'd see that. There's nothing about loading today that's any different of a stress environment than the loading we did on the launch attempt day. So we don't expect to see more things crack. I guess if the repair itself didn't do its job, then we might see a problem there, but nobody expects that to be. So yeah, nothing's going to be obvious. One of the other catches is because the skin temperature, these strain gauges are put right on the skin of the inner tank, which is half an inch, if less than that, away from the liquid oxygen tank at minus 400 degrees. The data needs to be temperature compensated. So there's thermocouples there. So the raw data coming out of the strain gauges isn't going to be too meaningful until they have a chance to process that data. Now all that's going to happen, I think we're generating, I lost track when they went over 5 or 6 terabytes worth of data. And all that's going to be post-processed and shipped to the Michoud Assembly Facility and the Marshall Space Flight Center, where the analysis will be done. That data will be there tonight. The expectation is by the weekend we'll have reviewed all that, and as you guys know, we decided we were going to roll back to the VAB, and so one of the no-goes for that rollback is a report from that instrumentation team that they are happy with the data. That doesn't mean we've analyzed it and the results of the data are good, but that we captured good data. The quality of it is fine. The sample rates are good. We didn't have a data gathering problem. And then we're not going to remove the instrumentation, but we can cut the wiring and then deconfigure the vehicle and be ready to roll back. So that's going to happen on Sunday, and our big picture plan is probably then Monday, Tuesday next week we'll start to get the results of that data in. It's going to take a while before we get all the fine details, but the big picture, are there non-linearities, is the left and the right good, all that's going to happen early next week, and we'll be talking about that as a program as we hit next week. Okay, but if we can get back to the rollback in a second, I just want to ask you, there were kind of 2 main tests that you guys talked about on December 3rd that when you really decided you needed more time, you needed more data
before you can make another launch attempt. The tanking test was one of them. The other thing was mock-ups that you were going to be doing at the Michoud Assembly Facility in outside New Orleans. How's that been progressing?
Actually, very well. That's been a big pause. Like I said, yesterday we talked. So 2 weeks ago we decided we needed to do the instrument tanking test. This week we talked, and on that fishbone we're able to eliminate a whole lot of things, and all that component level testing is really the main contributor to being able to remove things off that fishbone. So at the Michoud Assembly Facility, they've been doing a lot of coupon testing on stringer pieces to find how you could induce a flaw. They've been doing fastener checks. So did the act of installing these fasteners, these high lock fasteners, or the GP lock bolts that we put on the stringer to bolt it to the sheet metal. Did the act of installing one of those cause a damaged site, a flaw, a ding that could propagate? That testing's all been going really well and showing that it's very difficult to cause a problem that would have caused this magnitude of a failure that would have not been caught at MAF before they shipped the tank to us. At Marshall Space Flight Center, they're mocking up single stringers and 3 stringer panels, and they're going to basically go induce flaws. So what we've kind of determined on the fishbone is the real big area that's left as a contributor, the most probable cause grouping, is the assembly and manufacture and processing of the tank. These stringers are put on, basically there's a 4-foot wide by 21-foot long piece of sheet metal. Those 2 4-foot panels have stringers bolted to them, riveted to them. They're then joined in to make one big 8-foot panel, and then that becomes a panel of the inner tank, and there's 8 total panels on that inner tank. The 2 right next to the SRBs are called thrust panels. Those are actually solid machined aluminum, so they're a different family altogether than the panels that are out in the acreage of the inner tank.
And they take the most stress during launch, is that correct?
Yeah, they're the main load path. In fact, it's one of the things you don't obviously see when you look at the external tank. You kind of probably think it's just the ox tank, it's the fuel tank, it's just the big fuel tank. It's the main structural backbone of the entire stack. There's a thrust beam that runs through that inner tank that connects the left and the right SRB boosters together. And then that thrust and load is carried through the thrust panel down into the hydrogen tank, which is holding on the orbiter. So the orbiter is basically bolted to the top of the inner tank, or at the bottom of the inner tank. Sorry, with the nose, and then at the base of the orbiter down by the bottom of the hydrogen tank. All this is held to the pad with 4 bolts per SRB holding the SRBs to the launch pad. Nothing else is affixed to the launch pad. So the SRBs are held down. The external tank's holding them up, and then the orbiter's hung off the side of the external tank. So it's a truly complicated piece of machinery, even though it's just a big piece of metal with some fuel tanks on it. It's the main structural path for the vehicle. So anyway, those stringer tests are really defined that when you build it up, you could induce some stress. So you might not have cracked the part, which it doesn't look like we did. All our paperwork and all our processes show that a crack would have been caught. And like I said, the fractography of the failed piece showed that a crack was not there. So it looks like what we probably had happen was during assembly we introduced stress such that this part was kind of preloaded with some stress, and then the extra stress of cryo loading was enough to then break it and exceed its capacity. When you bolt this down, you kind of clamp it together. That clamping, there could be gaps between the parts such that when you then rivet it up with I think the lock bolts that we put in are something like a 5,000-pound force load, that you could trap a lot of that force into the part if there's a gap. We've learned that on this particular panel, the half panels right next to the thrust panels have doublers. So in addition to the big main sheet of sheet metal, there's a second piece. In fact, there's also a third piece on some of the stringers to give it extra reinforcement. And if you think about it, that's where the main thrust load's coming in. So those doublers are kind of there in a Y shape to distribute that thrust throughout the LOX tank, not just concentrated on one particular panel. One of those shims goes into that panel early in the assembly process. It's kind of sandwiched together such that when you then go bolt the stringers on later, you can't see physically where that cord and that shim meet up. And if you have a gap back there, you could induce some stress. We've done this, nothing's changed in the process. This is the way we've always done it. So there's probably been exceedances and gaps a little higher than we probably needed them to be all along, but it's one of the things that then stack up. And so when you stack up that there might have been a gap there, and you stack up that you might have clamped it down a little too hard, which made the feet splay out a little, and then when you look at the stringer itself, this particular stringer based on the x-rays is about it's hard to see, but it's like 1/10 of an inch, a little further north on the tank, up the tank, than the other stringers, which means these things are preformed with a bend in them. That bend is now in a different place than it was supposed to be. So on these half panels, you have these groupings of things that if they line up on you, could cause a problem. That's what the big three-stringer and single-stringer tests at Marshall are going to be for, is to go put those flaws, manufacturing defects, so to speak, into a panel, and then load it and see if that's big enough and can cause the stresses we need to recreate the failure we had. So kind of the proof of the pudding, so to speak, of our theory of what could happen really can happen, and that could be our most probable contributor to the problem that we've had today. So all that says is, we're not probably going to come out of here with a smoking gun, but we're going to come out of here with a family of failures, and we're going to have a lot of testing to then make sure we're not fooling ourselves that we kind of picked the one that matches what we see. Go really prove that it can match what you see.
And we're talking with Mike Moses, Space Shuttle Program Launch Integration Manager, and we're about 32 minutes into the tanking test for Space Shuttle Discovery's STS-133 mission. The video we have right up there now, you'd touched on there a second ago. Let's see, you just started out the tanking on time at 7 a.m. and the liquid hydrogen started the slow fill process at 7:12 a.m. That picture we were seeing there a minute ago was actually the dots you were talking to. Some of the which are used for the high. It's basically 3D. If you go through, if you could just talk about it for a second, it's 3D. High resolution cameras. You put more than 10,000 little black dots on the section of the tank.
Yeah, a whole lot of dots.
Hand put, by the way.
Yep, finger painting. We did finger painting. So the area you're looking at the camera right now, that's actually the panel 2, which is where the damage was. So that's actually where the cracked stringers were. And you can kind of tell the new white-looking foam hasn't had a chance to age in the sun and get orange yet, because we keep taking it back off and doing other things to it.
Right.
So we took that area back off, and we went in and added all the instrumentation. That's the big copper-colored cables you see running in and out there. And then when we sprayed the new foam on, the dots are basically for this photogrammetry technique, which is really you have a set of cameras that are offset from each other. So there's a stereoscopic camera, 2 cameras pointing at the same place with a known baseline distance between them, focused on this area. And what they'll do is they'll be able to then measure the movement of this zone. So each of these dots kind of allows them to track what one camera sees where the dot goes versus where the other camera sees the dot goes, and you'll be able to create a 3D mapping of how this flange shrinks and potentially rotates. One of the other things we're worried about is the flange. We know it shrinks but some of the modeling shows that it won't shrink uniformly, so it might rotate a little bit. And if we add that rotational load into the stringer loading and not just a simple moving in and out in a single plane, then you don't need nearly as big of a flaw to cause the problem, because that's a much higher coupled load now if there's a rotational component to it as well. So that's data we're really looking to get. And one of the ways to do it would have been to strip foam off of a whole lot of the flange and add a whole bunch of strain gauges. And the teams came up, it was actually the Glenn Research Center had done this technique before for us in the shuttle program, back with return to flight, to help with some of the RCC, the wing leading edge imagery. And so this technique was much easier, much less intrusive, even though it required painting a whole lot of dots on the side of the tank. So this you're seeing here on panel 2, on the kind of around the backside over by where the gup is, we painted a much bigger area with, I think it's something like 27,000 dots. Over on panel 6 to gather more data back on that side. The reason we kind of split between the two is here on the front side of the tank, we are worried about debris. This is a very critical debris zone, and that paint would then, if foam wanted to pop off in what we call popcorning, which is little tiny pieces of foam that have little tiny air pockets that just kind of, as you go up through the atmosphere, they literally pop off like a piece of popcorn. No debris risk at all, but if there's a glob of paint on top of that, you'll now lump up some popcorn together and you could pull off a bigger piece of foam. So before we fly, we will strip that foam back off and remove those dots. But on the back side of the tank, we can leave those dots in place. So we dotted up a much bigger area back there to gather even more data in a debris zone that's not a risk to us. So that's the 3D imagery. So we talked about the strain gauges and the thermocouples. There's this 3D imagery. And then finally, the last piece of data is really after we finish tanking, we're going to go X-ray and take X-rays again of this flange to make sure no cracks have occurred that didn't cause the foam to crack. You know, you could have a smaller crack that might not be big enough to make the foam itself displace, but we want to make sure we don't have any of those. One of the things we're going to go back to the VAB for is to look at the back side of the tank. We call it the minus Z side. It's the part that doesn't have the orbiter on it. We've never been able to look at that since this first crack appeared, so this will give us a chance to take a look at the back side. We've kind of always thought we might need to do that. We were kind of waiting for some of the analysis to show structurally did we need to do that. This is kind of two problems, right? If the stringer pops structurally, that's not supposed to happen, so did you structurally compromise your tank? And then next to the orbiter, if the foam cracks, now you've displaced it, you could lose a piece of foam. That's a very big deal from a debris standpoint. Our analysis is showing that if the foam does crack, that's a concern, and we cannot live with that. And so we know that we can't have a problem on the front side of the tank. On the back side, the analysis was coming in to show that we could probably fail two stringers, have two stringers next to each other that crack like this, and structurally we'll still be fine. But three in a row would be a problem. But there's some fuzz in that model. There's some assumptions in that model. And then ultimately you got to kind of play the card too of if we have more cracks than just this one, even though they didn't break the foam, that might make us reevaluate some of this fishbone analysis, this root cause analysis to say, you know, do we truly understand that we could have had so many manufacturing defects all just on one tank? And so we are going to go get that data. And we are going to ND the backside of the tank just to make sure there's no cracks back there. So both from the previous loading and this loading, we'll be able to look at all the stringers on the flange to make sure they've all performed properly. We'll be able to then detail inspect the repair that we did, make sure it performed properly, and kind of just put that feather in our cap to say that we don't have any other problems on this tank. So that's I think I'm answering your next question is heading back to the VAB.
So your plan is to do this non-destructive evaluation techniques, this basically X-raying of underneath the foam, the entire inner tank area, which you haven't been able to do.
Yeah, 360 degrees around. And
you'll take the dots, and you'll basically strip the foam off, get the instrumentation off that you put on in the past week, take that off in the vehicle assembly building, and then what possibly, depending on what data you get, you might are modifications possibly in the cards, or?
Yeah, that's certainly possible. You know, we need to take the instrumentation back off because well, A, we don't want the wiring sticking out, and B, the you know, these things are bonded to the metal and then the foam's put on top of that. That's not a certified configuration. We could probably go off and certify it's okay to leave these instrumentation stickers on the tank, but it's easier to actually just take them back off again, and then so we'll re-foam out that area and close it out one more time. But the results of this test, the results of all the 3-stringer testing at Marshall and at Michoud, the results of the single-stringer coupon testing, all the fishbone analysis, all the Nastran modeling and computer modeling, all that is going to feed into our ability to determine whether we have acceptable rationale to fly, that this tank is good. If at the end of the day we come out with an answer that says there's some things here we can't control. So there's two pieces, right? There's can we find a root cause enough to know why this happened? And we're getting much smarter as we go every day. We're 100 times smarter than we were a week ago, and we're 1,000 times smarter than we were when the failure first happened. So that's coming along really nicely. We're gonna come up with some most probable causes. The next piece is, can you screen those ahead of time? So you now know what might have caused it. Can you go show that you're not going to have it happen again? We initially thought, you know, again, in that an easy way to get to flight rationale would be the cryo loading. So if you think about it, there's two kind of loads that go in this tank. There's the shrinking, which pulls the stringers in, and then there's ascent, and the fact that these stringers are helping hold up a tank full of liquid oxygen, millions of gallons of liquid oxygen sitting in, and then we're going to accelerate that up through the atmosphere. So axially, we're putting a lot of load down the tank. And so does the loading of cryo put a stress in the part that's big enough such that if it had this manufacturing flaw, had these stack up of tolerances, that it would break at loading as opposed to breaking during ascent? Can we screen this, say, if we fill it up with cryo, X-ray it to make sure it didn't break, we know it won't break after that? If that answer was true, we'd be in really good shape and we could then go fly. It turns out that answer is not completely true. It is true for some of the fasteners on this stringer. The first couple, see the loading pulling that stringer in. Obviously, if you think about it, you get this 21-foot long piece of metal that's trying to bend in. The very end of it's going to see the highest stress. So those are getting the highest load from cryotanking. But the next couple right below it are seeing a highest load from ascent, and that load. And then the rivets down below that are actually in compression, and cracks can't propagate in compression, so they don't become a problem for us. So the answer is not a clean one, so we don't have a complete screen. So now you got to look at how are we going to build risk acceptance rationale to fly. At the end of the day, we're not going to be able to completely control the problem. And so we are talking about potential modifications that would allow us to control pieces that we can't or we don't understand well enough, or that are too big of a risk to us. Again, these high debris areas are a big risk for us, and then structurally we're looking at the areas next to the thrust panel as one of the main load carrying paths, so that's an area we wanted to concentrate on as well. So we are talking about potential mods. The teams are working in parallel on that. We have a few on the plate. We talked those yesterday at the program level. What we're looking at potentially doing, if the data shows that we need to, would be to basically go in and add what we're calling radius blocks, which are basically doublers along the rivet line for about 36 stringers that are in this region where this shim I was talking about that's between the doubler that you can't see. That seems to be our highest risk area, or I should say the highest probability that if we're going to have stack up of problems, that's where it's going to occur. So we can kind of take that part out of the equation if we reinforce that area. We have to make sure that reinforcement doesn't have unintended consequences by stiffening up a part, changing the design, changing the overall load path. And so there's still a lot of homework to do before we say go put that mod on the tank. But it has a lot of potential to then take a big piece of the risk off the table for us, leaving us with something left that would probably then be acceptable and have a path to get towards flight rationale. So we are going to talk about that. The results of this tanking test are going to do a lot to help us with that. The stringer testing at Marshall. You might see us schedule-wise, we're going to have to we've been talking a lot about doing the mod because we need to be ready to if the data shows us to. That would be occurring next year, or in January. So we'll see how that goes.
It's next year. Yeah.
Next year. Yeah, it just seems dramatic when you call it next year. But, there's still a lot of work being done. We're going to have folks working around the country right through the Christmas holiday here to be ready to potentially fly again in this February launch window when it comes around.
So this would, if everything lines up, you get the data that you're hoping to get. If the modifications are necessary, you would look to bring Discovery back to the launch pad somewhere mid next month.
Yeah, it'd be mid-January time frame. The date moves around, but it's in the 13, 14, 15-ish time frame. Within a week of that milestone, we'd head back out to the pad. That would be to be able to set us up for a February 3rd launch attempt. That window I think runs from February 3rd to the 10th, I believe, is the length of that window, and then another one opens back up on the 27th. There's nothing magic about having to make that first February window. It's just so, it's schedule awareness. So we need to head back to the pad mid-January to be able to be ready for the first window. If we can, we will do that. If we can't, we won't, and we'll stay until the next opportunity. So that's just kind of the milestones in front of us on what potentially is next for us, both in the VAB and then when we get back out to the pad.
Okay. Well, Mike, thank you for taking a lot more time than I was that I thought I was going to be able to squeeze out of you and walking us through this, because it really does help us to get a better understanding with this entire. It's a tanking test, and that sounds very simple. But when you start talking tens of thousands of dots and HD cameras and 90 plus sensors on the tank, it's a fairly complex tanking test, much more elaborate than we did last year, like you said, with the GUP tanking test in July 1st, where it was just a GUP leaks or GUP doesn't leak.
Yeah, that was just a fill it up and see if it leaks, and this one is definitely much more complicated. It's going to generate a lot of data that we've not had when we were first laying this out to the external tank project. Down here we're thinking, okay, we had a structural problem. They're going to want strain gauges all over the place to see how structurally the materials responded. And they first came in with, that's all great, but we really want a bunch of thermocouples. And you need to temperature compensate. The actual thermal profile that this part sees as the cryo loads it up isn't measured because we don't do full-scale testing. So we don't have a lot of data to validate that part of the model, and a lot of the uncertainties in the model are in what thermal assumptions are you putting in there. So just having that data alone is going to really help refine the answers. It's not going to change the answer, but it's going to give us a much more accurate answer. And so there's things you learn like that as you go through this process to really kind of understand other ways. And then this photogrammetry technique almost seems like black magic, but it works really good in the lab. This is the first time we've done it on such a large-scale object that's actually sitting out in the environment. Not only is the tank going to be moving in the wind and moving as it shrinks as it's loaded, but the cameras on the service structure are going to be moving. Being able to back out the data, one of the reasons they want so many dots is it helps them take those uncertainties back out. It's going to be really interesting to see. None of this is mandatory data. It's all just building in the direction of goodness. So if for some reason we don't get great data out of that photogrammetry stuff, that's okay. If we have a couple thermocouples and a couple strain gauges that stop performing, that's okay. It's not. We have some redundancy built in. It's not the end of the day, and it's really kind of going to be a building block process as we go. We're not committing to flying anytime soon. We got to wait until we know we have a good answer to go fly. We want to make sure we know the risk we have in front of us and not have any unknown risks out there.
Okay. Well, Mike Moses, the Space Shuttle Program Launch Integration Manager, thank you for talking to us now. We'll actually look to have you come on and summarize what you've seen a little after the fueling part and when the final inspection team is out doing its thing out on the launch pad before we wrap up our commentary this morning. About 10:50 a.m. We'll have you come back if you would mind and see what's been seen so far as you're building towards the direction of goodness, as you said.
Yeah, no problem. And I'll see if I can bend your ear even more with more data.
I'm looking forward to it. All right, Mike, thank you for joining us. And again, we'll just quickly recap. We are in the we started the tanking test. The fueling process did begin on time at 7 a.m. Eastern. Liquid hydrogen slow fill started at 7:12 a.m. And we are currently in the simulated tanking test countdown at T-minus 5 hours, 12 minutes, and 15 seconds. We'll pause for a couple minutes and give you more tanking test data in a few minutes. This is NASA Public Affairs at the Kennedy Space Center.